So hello everyone. So today is the first lecture of data structure and algorithms. So let me first clarify the what's the goal of this thing, why we're doing it. So the goal of this class is basically to teach you how to solve the problems, how to solve particularly computational problems. So what's the meaning of a computational problem? So loosely speaking, anything that involves to do some computation, maybe a mathematical computation, can be treated as a computational problem. So in if you see it mathematically, what function basically is, it takes an input and then it gives an output. Okay, so let's suppose we had some 1, 2, 3, and 4 inputs. Let's suppose we had some outputs corresponding to those. Okay, it's sort of a binary relation if you see it in there. So it's a binary relation. Okay, so now for an algorithm, we'll have some set of inputs and it will give us set of outputs. So that's what the whole point of this course will be. So we'll be solving computational problems. And one more thing, additionally, we'll be solving them with efficiency. So if there is a problem, we'll find a solution and afterward we'll try to make it efficient. We'll formalize what is the meaning of efficiency and stuff like this. So all of these will be formalized and then we can sort of code these in our computer and then do the, let's suppose some testing and stuff like that. Generally, I tell you first what an algorithm means. So we'll code the definition of algorithms and then we'll start with the main topic of today, that is time and space complexity, and we'll see what these things are. First, let's see what an algorithm is. Okay, I'll just keep on changing the color so that it will look at least better. So informally, an algorithm is actually a well-defined computational procedure, okay, that takes some values and it gives some output. So it is a well-defined computational procedure. Okay, which takes some input and in finite time gives some output. Okay, I just underline some of these things. The first thing is a well defined procedure. Okay, the second thing is it takes finite time. Okay, if you ask me what an algorithm means, that means, for example, if you give me some input and on a finite time, on this input within a finite time, I should be able to give an correct output. Okay, that I call an algorithm. So there will be a stepwise procedure. Let's take an example. A simple example would be making a cup of tea. Making a cup of tea, let's suppose. Okay, if we have to make a cup of tea, we'll follow some standard procedure. Let's suppose the first thing that we'll find is the first thing is find a utensil. Okay, and then second step would be, let's say, pour some water into the utensil. And then third step will be put the utensil on the gas or something like this. Utensil on the gas, and so on. So there will be other steps and it will sort of finish somewhere. So that's what I mean by an algorithm. So algorithm will be, loosely speaking, a stepwise procedure. So here we are solving a, let's suppose this also is a computational problem. This making a tea is a computational problem. So in a similar fashion, if we have some problem where we want to get some output from a particular input, and we'll follow a stepwise procedure. In a computational sense, what will be a problem? So we'll have, let's suppose we'll have sorting problem. So in sorting problem, so we'll have some input. Let's say we'll have input a1, a2 till, let's suppose, an. Let's suppose these are n numbers and we want to sort them. So what is the sorting problem? So problem here will be So problem will be to find a permutation. To find a permutation, permutation basically means a reordering of these numbers. You'll have to reorder them. So find a permutation of inputs. What are the input is? Let's call this input, such that it will be either in ascending or descending order, such that we'll have something like this: a1 dash, let's suppose, is less than equal to a2 dash, and so on, an dash. This is our permutation. We'll find a permutation. That permutation will be a1 dash, a2 dash, and so on, an dash, such that they follow this. Basically what I'm saying, if I have numbers 1 2 4 6 8 9, something like this, if I have to sort this, so this is my input. So what will be the output? So the output will be 1 2 4 6 8 and 9. This will be output. And whatever the procedure that will do this, so it should be a stepwise procedure. The first thing is that, and it should be able to achieve it in finite time. Okay, it should give me the correct answer as well. So output should not be incorrect. So this is called an instance. So when you have a procedure which you can apply on any sort of instances, so you can give me a generic implementation of an algorithm. So I'll give you some input and you'll give me some output, and then one of the example is called an instance. This is one instance of an algorithm. I don't want to bore you with mathematical details and stuff like this. Just have this in your mind. The algorithm is basically a thing, a stepwise procedure by the help of which we solve computational problems. And the important thing that I told you is that it should be well defined, so there should be no ambiguity. And the second thing, it should take finite time. And you know that there are algorithms which give incorrect output as well, but they take finite time. And sometimes this algorithm also important. So you might be hearing this for the first time, that the algorithms which are giving output as incorrect answer, they are also important, but we control the error rate, because sometimes a problem is such that we are not able to find its correct solution within a bound of time. So what we do is we'll write an incorrect algorithm, and which gives an incorrect answer within certain range, but that incorrect algorithm is better than the correct algorithm, because let's suppose correct algorithm takes 300 years, and our incorrect algorithm takes, let's suppose, 30 minutes to give the answer, but it is within a certain range of the inaccuracy. Inaccuracy, that's what I mean. So algorithm should be well defined, there should be no ambiguity, and second thing, it should take finite time, and preferably it should give us the correct output. That is the definition of what an algorithm is. Before going into data structures, I would first like to introduce some basic concepts, so that you understand what the data structures are, why is the necessity of data structures, and things. So the first thing that I'll introduce is variables. I hope everybody knows them, but just for the completion purposes, so that everybody is on the same page, I'll introduce these variables. Please stop me if you have any confusions anywhere, so that we'll clarify it then and there, and we can move ahead. What is a variable? So before going into the definition of, like, in computer science, what a variable means, so we'll see in a mathematical sense what a variable is. If I write an equation, let's suppose x cube plus 3y plus 4z is equal to something like this. So you have been taught from the childhood onwards that whatever takes value which is varied. So let's suppose this x, you can give it any value. This y, you can give it any value. This z, let's suppose, you can give it some value. Okay, and then you will get an output for this. So these x, this y, and this z are called variables. Okay, so variables are the values, or placeholders we'll call them. So they are placeholders. Placeholders means, so they'll attain some value, so they don't have fixed value. That's why they're called variables. That's their value varies. Sometimes in this equation, let's suppose x will take value 1, x will take, in the other equation, x will take value 2, or something like this. So these are variables. So that's how we see the variables in the computer science also. So they basically are names of the addresses. So if you see in computer science, if you are from C background, you write something like int a, you declare a variable. So what are you declaring basically is a memory space. You are saying I am naming a memory as a, so there will be some memory in our computer, so that will take a chunk of memory and we'll name it as a. Okay, something like this. So this is a variable. The second important concept is now data types. So we'll see what data types are, then we can move on to data structures. So what are data types? Data types. Now you have these variables. So variables, in nutshell, what I'll say is they are the names of memory locations, memory address. So there we have memory and it has an address and we name it. Okay, names of memory locations, because you have to store something in the memory location and you have to name it. That's why in C, C++, Java, even you declare the variable name. Let's suppose int, string, or maybe character or something like that. So what is now a data type? So now in order to save a certain thing in the memory. So because if you see, we have different types of data. We have numeric data. Within numeric we have float, integer, and stuff like this, and then we have textual data. Okay, so if you see, we have numeric type data in which we have integers. Integers means minus infinity to infinity with discrete values. So we'll have this -1, 4, something like this. Okay, then we have some real numbers, 0.1, 0.5. Okay, and then we can also have, let's suppose, some imaginary numbers or things like that. So these all are numeric data types. So in order to tell the computer that you are storing something which is numeric, you have to give it a hint. Okay, even when you try to open different programs or different types of files in your computer, so there is an extension which you might have seen. For in image it is .jpeg, or in your video it is .mp4. So what is extensions tell? Because there are certain programs that will read this files. So you are telling your computer that these are the files that I have stored, and you have to choose a specific program to open these files. Okay. In the similar fashion, when you are storing something, because after all everything is binary, but how to read it becomes the question now. So in our data types, we can store numeric data types. We can store numbers like 1, 2, like these integers, like rational numbers. Sometimes even imaginary numbers like 2 plus 5 iota. And within these numeric numbers, there are a lot of types of types of these numbers. So the first thing that we saw is integer, then we saw float, and then we can have other, like how much precision do we want, and then we can have this string values, characters, and things like that. So all these things are called as data types. So in a simple language, so what a data type is? So anything that this memory location takes value of. So it can take value as an integer, it can take value as an int, it can float, or it can take value as double or something like that. So all these values which are predefined are called as primitive data types. Primitive data types. So what are these? So these are predefined. So when you start programming in any language, so there are these data types which are predefined, like integer, there is float, then there is double, okay, then there is string, character, and things like that. Okay, and then we have something called as user defined data types. User defined data types. What are these primitive data types? They have predefined meaning. So if you say integer, so integer 2 means you are going to do something with number 2, and you are going to manipulate in a certain way. If you have two integers, like 2 and 4, so if you have you can add these numbers, you can multiply these numbers. Okay, so with primitive data types you have some operations also. So primitive data types plus operations. On these numeric numbers you have operations like logical operations, you have arithmetic operations. Okay, and then maybe you have a relation operator and some other operations as well. With a user defined data type, so user has now the ability to define data types. So initially you only can work with int, float, double, or maybe character. Some few data types will be there which a language will provide. Okay, then what are user defined data types? They are the data types which user will define. So now user has certain requirements, and he wants to define a user data type so that it does some job. And on top of that, he also defines some operations that we can perform. Okay, so that's if you have seen in let's suppose in C or C++, so there we have something called as struct. Okay, we write struct and then we add some data into that. And this is what a data structure can be thought of. So in data structure, so based on our discussion that we had so far, we had variables first, and variables were the names of memory locations, and then we had some data types, that is the type of data that we want to store. So language, they offer us primitive data types, or what we call as system defined data types. So like integer, float is there. And what's the difference between them? They have a certain range and different precision. I hope that you know all of this stuff. So that's why I'm not going into detail of these things. And then we have user defined data types. So that is, sometimes we feel that these primitive data types, that they are not enough for us, we need some more things. And then users are given control, and users are allowed to make their own data types. And I gave an example of C, C++, where you have the struct, and where you can make this. And then even in Python, and which are object oriented language, we have something called as class. So in class, that class gives us the opportunity, or the class gives us that capability by which we can create our own data types. Okay. Now let's go into the data structures, and we'll formally define data structures. Is everybody with me?
Yes, sir.
It's really hard time to the first thing is to wake up and then to attend the class in the morning, and even it is difficult for me as well.
Thank you, sir.
I hope this discussion is clear. We started with variables, and then we saw that how the system defines something called as system defined data structures, data types. And then we saw how user is being allowed to create some new data types, and then we'll come with the data structures. Okay. Now we need some mechanism for manipulating the data, okay, to solve our problems. So this is what data structure comes in to rescue us. So it's a particular way of storing and organizing data. Okay, we store it in a particular fashion, and we organize it in a particular fashion so that we can use it efficiently. So what is a data structure? So it's a it these provides the mechanism. So these are basically the memory locations again. They are like variables, so we'll just store some data into them. So they provide us the mechanism. They provide the mechanism for manipulating and organizing data, and organizing data in a certain way. Let me give a physical example now. Let's suppose if you are in your house right now, so if you have to drink water, so you have to drink water, what you will do is you will pick up the jug, and maybe you'll drink water by the glass. The whole thing is you need water. Let's suppose water, let's consider water as data. Okay, you need water, and you need to do something with water, because water can be used in different ways. So you can use it for drinking, because you need to drink it. So drinking, maybe let's suppose, is one of the operations. Okay, you can use it to wash. Okay, let's take these two instances. So if you have to drink water, obviously you'll take a glass. So what glass is? Glass now stores this water in a certain way, and you drink from the glass in a certain way. So this glass can be thought as a data structure, because water is our data, and this is the operation that we are doing on it. Drinking is the operation, and this glass is the storage where we keep the water. And if you have to wash, for example, let's suppose you have to take a bath, you have to wash yourself. So what will happen? You will take this water into a bucket. Now bucket is a data structure. Okay, again you'll wash, maybe you'll take a bath from this water. Now bucket, you have stored it in this, and from the bucket you will again take it via some mug, and you'll use it. You'll use mug to, let's suppose, mug, bucket plus mug. This is our data structure, and maybe this is our, let's suppose, certain manipulation thing by which we can manipulate our data. And I'm considering this water here as data. This is my data, this water, and these are the operations I want to perform on it. These are the operations. This is the problem that I'm solving. These are our data structures. Data structures. This is the analogy I'm giving. So we had water, so we had certain purpose. We had to perform some operation, maybe drinking, maybe washing, cleaning, or things like that. So I gave an example. If you have to drink water, so you'll drink it in glass. So you'll store the water in glass, and then you'll perform the operation. And if you have to take a bath, then what you'll do? You will store the water in a bucket, and then you'll use mug to take water out of the bucket. So here you see that we have different ways to store this data, and then you perform the different operations even on that. Similarly, in the real world scenarios, when you have data and you want to perform something on the data, okay, you have data. Let's suppose you have a text document. Okay, this is your text document. If you have a text document, let's suppose on the operation you want to count all the number of, let's suppose, is will be a word in the document, and you want to calculate how many edges are there in the document. You want to compute the frequency of this. And this is, then you will store this document somewhere. Okay, this is when you're operating on it, you'll store the document in a certain way so that you can perform an operation on this and you can count the frequency of this is. Okay, so this is the example. So now how to store this? Okay, how to store it so that manipulation becomes easy. That is where data structures come in. That's what I told you. They provide us the mechanism. The first thing is they'll store data in a particular fashion, and then they'll provide us the mechanisms of manipulating and organizing this data which we store. Okay, now based on this, we have two types of data structures. The first thing is called as linear data structure. Linear data structure. And obviously, second thing will be called as non-linear. How many? So I said that we have now two types of data structures. The first data structure is called as linear data structure, and the second is called as non-linear. So what is linear? So if the elements are, I'll say an entity. When we store something, we'll call it an element or an entity. If the elements are accessed in a sequential order, okay, if the access is done in a sequential manner, if access is done in sequential manner, okay, what is the meaning of sequential manner? So for example, if you store an array, let's suppose, I'll assume that you know a bit of array. So you will store something like this: one, after that two, after that three, after that four, and you can access the elements in a certain order. So you can access this and then this, and you can access in a certain way. For example, if you have even linked list, there also you have certain order in that. You can access them sequentially. Linked lists are there, stacks, queues, all of these are linear data structures because you store them linearly. Then you have non-linear data structures. Okay, so these are data structures which have non-linear order. Let's suppose trees and graphs. So you cannot access them sequentially. So where to write it? I'll write it here. So elements of this data structure are stored or accessed in non-linear order. So we store slash access them in non-linear fashion. I hope that you understand what's the meaning of linearity and non-linearity. By linear, I mean you can go element wise, one first element, then second element, then third, then fourth, then fifth, and things like this. So if there is a possibility where you can go like this, that we can say that this data set is linear. If there is no tree, is like something like this. Okay, I'll just make this, and trees are much bigger than this. So here you will store or you will access the data in a non-linear fashion. These are two types of data structures. So again, to reiterate, what is the data structure? So these are the, what you can call, these are buckets or something where we store the data and organize data, and it gives us operations by the help of which we manipulate the data. And then there are two types of data structures. One is called linear. So linear data structure means where elements are accessed in a sequential order, but it's not compulsory that you will store them in a sequential order. Okay, for example, in linked list you don't store them sequentially. You store it one node, the linked list somewhere, and then a second node will be stored somewhere else. Okay, but you will access them sequentially, and you can access them sequentially. And then non-linear data structure is the type of data structure where we can store or access the data in a non-linear. Examples are trees and graphs. Okay, so I think I'm clear with what an algorithm is. Okay, algorithm is a computational procedure by the help of which we solve a computational problem, and it should give us preferably correct answer, and it should give that answer in a finite time. Now the important topic for the day is how to analyze these algorithms. Now we'll be going with the data structures, and then we'll be seeing, okay, we take this much of time, we take this much of space, and how to first quantify their time and space. Okay, that's the topic that I wanted to cover. So we want to analyze the algorithm. That's called analysis of algorithms. So analysis of algorithms. So if you remember in the previous session also, I told you, if you have to analyze an algorithm, so if you have to see which algorithm is better, how to compute this efficiency, so you have to quantify this thing. You have to have a metric. Okay, and for that we should analyze the algorithm. The first analysis part that we'll be do is we'll do the running time analysis. Okay, analysis on running time. So we'll do running time analysis. Okay, so what is this running time analysis? So it's the process of determining, for example, within a certain input, if we increase the input, so how will be the what time how will the time get increased? So if you have a certain input and you are performing an operation in certain time, so if you increase the size of the input, so how will the algorithm behave? So how much more time will the algorithm take? So that analyst will have to do. Okay, so but for that, the first thing that will come into your mind is that maybe we can compare algorithms based on execution time. So we'll see how much time does it take, execution time. But if you take this execution time, the first problem it has, it will be machine dependent. For example, let's suppose Amir has really fast machine, and let's suppose Rian has a slower machine. So if you run same algorithm on both the machines, they'll show different execution times. Okay, so this execution time then cannot be used to compare algorithms. So it's not a good measure. Why? Because it is machine dependent. The first thing is I want to compute a metric. I want to come up with a metric so that I can compare algorithms in terms of their efficiency. The first thing is running time. So I'm saying I cannot use the execution time, the clock time. So if I run an algorithm on a machine and I'll see how much time does it take on a machine, and then maybe I can say this is faster. But what I'm saying, the problem with that is it is machine dependent. It is hardware dependent. The second thing is we can see the number of statements executed. Number of statements executed. We could also use this, but this is again not a good measure. Why? Because it varies from a programming language. It is programming language dependent. So if you write a code in Python, you will just write few lines. If you write code in C, there will be much more lines. Okay, so you cannot just count the number of statements and then you will say if an algorithm has more number of statements to execute, it means it is not good algorithm. Okay, then what is the ideal solution? How to quantify this? So now we are in a dilemma, how to quantify this algorithm. So if you have some algorithm and we want to see how does it perform, so that now becomes a problem for us. Okay, if you see the problem right here, how many of you are able to see like there is a problem that we have to follow, that we have to find an answer for? Because execution time we cannot use because it's machine dependent. The second thing is if you have to use this number of statement execute, again there is a problem of language dependent. So we have to come up with some model so that it is machine. The first thing is it should be machine independent. We should not be dependent on the machine. So we should give some notion how faster this algorithm will run. Okay, and it should not be even dependent on the number of statements executed. If we write in a particular, it should be language independent. So this should not always also be the case. So we have to come up with a model first. So for that, let's understand a bit about how computers memory work and how what's the model of computation we assume, and then we'll see how to quantify this thing. So I'll write model of computation. Why am I teaching you all of this theory? Because this becomes really important when you analyze the algorithms. Let's suppose you will code something. I don't want you to be the coders who don't know what the algorithm, how much time the algorithm will take roughly. It won't be like you will exactly pinpoint this algorithm will take 1 hour of time. But you can say this algorithm is better than this. Why? Because based on this. Okay, so you should tell that because you have to write efficient code. So here I'll write model of computation. This will be a little bit theoretical class because why this is where I want to introduce you to the overall basic concept so that when we code something and you have an understanding of the things. So what's the model of computation that we use? So have you heard about word RAM? So how many of you have heard about word RAM? I think you have heard about RAM, that I am sure. What is a RAM?
Random
Random
access
access.
memory.
Okay, so random access memory basically tells me you can randomly access the memory. So randomly access means let's suppose this is a RAM stick. Okay, it is made up of like different memory units. Let's call them flip-flops or something, like it depends on the how RAM is implemented. So let's say this RAM is like this. It's basically an array of memory. So there are memory locations. Now you might have heard that your machine is 64-bit machine. Okay, this 64-bit means word size. This is called as word size. Okay, what is the 64 bit? It means that you club 64 bits. Let's suppose these much are 64 bits. You club these and you name them as one address. Okay, so your 64 bits are addressed. This is called as word addressable, because you'll have to address the memory. Whenever you store something, you'll have to have its address in order to access it. So what I'm saying is, so word RAM means, so we assume that the word size, let's suppose your machines are 64-bit machines. Sometimes you might have also heard 32-bit machines. So what's the meaning of 32-bit machine? That means that the size of that, the size of the smallest chunk of the memory which can be addressed is 32 bits. Let's say if you have say 128 bits and your machine is 64-bit word addressable, we call it. So there will be two memory locations, then one will be 64 and then other 64, and these two will be addressed. Okay, this is 64-bit. So what is the maximum number of addresses that you can address by using 64 bits? So that's 2 to the power 64. So these many addresses are the possible, and after that you cannot, and then you have to increase this word size. That's what I'm saying. I hope this concept is clear. I'm saying that, so if this memory basically is just a chunk of flip-flops, we have this binary bits, ones and zeros. So if you have to address something now, you'll have to have an address for something. So the least unit that we give address to is called a word. Okay, what is 64-bit? 64-bit means we are giving 64 bits one address. Okay, these are 64 bits, they'll have one address. After that we'll have 64 bits, they'll have one address. After that we'll have 64 bits, they'll have another address. Okay, is this clear?
Yes, sir.
We call it word
Yes, sir.
addressable. So we call this whole thing as, let's say this word addressable memory. So why am I telling you all of this stuff? Because now memory are, we have this addressable sequences of words, and this random access memory means you can randomly access any other. You cannot maybe access this. Why? Because this is with, you cannot address a bit, because now you have 64 bits you can address. You can maybe go to this location, you can go to this location. Okay, this is why it's called as randomly access memory, because you can randomly access this memory now. Okay, and what do we assume here? We make some assumptions. We say that certain operations like the integer operation, maybe some logical operation, bitwise operation, so they take some constant amount of time. So for example, we have different operations that our machine supports. So operations that we have, let's suppose arithmetic operations. So arithmetic, I'll write AP, arithmetic operations. Okay, we have addition, subtraction, multiplication, division, float, and a lot of things are there. And then we have logical operations. In logical we have logical and, we have logical or, it's a logical not, this, and then we have even bitwise operations and or things like this. And then we have, in operation can be read from the memory. Read is also an operation. We have write into the memory. This is also operation. Okay, read means basically access the memory. All of these, these operations, let's consider them. We'll make an assumption that they take constant amount of time. Okay, they'll take constant amount of time. This is the assumption we'll make. The first thing that I told you is we have this memory. This is the structure of memory. This model of computation we'll use. That is, we'll say that this is our word RAM. That is, it is word addressable. We have 64-bit size of the one word, and 64 bits will be given one address. Okay, and based on that, what we said is, then we have operations which will perform on the data. We'll perform operation like if we have integers, we can perform arithmetic operation, logical, bitwise. If we have to read something from data, and if we have to write something on the RAM. So these are the operations, and there can be many operations. So we are assuming that each of the operation will take constant amount of time. One operation will take, let's suppose, C time, some C, and this constant will be machine dependent. How the machine performs. Okay, now we'll have to sort of quantify this, how to compare these algorithms now. Okay. There, what we'll see is, we'll give these a constant value. Let's suppose if you are performing A is equal to B plus C. Okay, so if you see this here, this is this is one operation. So this plus is one operation. So now first what you will do is, you will read this B. Okay, then you will read this C, and even then you will load them into the RAM. Then you will add them together. Then you will again read A if there is something, and then you will assign this A, and you will see a lot of operations are there happening. And maybe primitively what we can do is, we can say whole of this can be considered as, let's suppose, it takes some constant time. Maybe if you see, it takes, for example, how many operations, the first read, then add them together, and then write it to a, roughly it takes 4 operations. So we'll say it takes 4c time. Okay, it takes 4 into constant, some constant time, 4 times constant. This again is n the constant, capital C. That's what I want you to understand. These operations, they take a constant number of, they take constant time. So if you have something like, let's suppose you perform this operation of n times, so you will say it takes n times c. Now it takes some n value. If you have this in the loop, okay, it will take n times of this. Is this clear? Is the model of computation clear? What I mean by model of computation?
Yes, sir.
Is this clear? Like operations, what is the assumption that we made? These operations will take constant amount of time.
Yes, sir.
Now we'll see what is called as rate of growth. Based on this discussion, we'll see what is called as rate of growth, and we'll see how will the algorithm grow, rates of growth. These are fundamental concepts, because whenever you are coding an algorithm, you must know how an algorithm will behave if you increase the input. So what is the rate of growth? The rate of growth is basically, which it means how will the running time increase if you increase the input of the function. So simply, what I can write is, it quantifies how running time of an algorithm will increase on increasing input. Okay, now please focus here more, because this is the main crux that whatever I taught you so far is because of this. I wanted you to understand this rate of growth. Okay, so if you increase input, so how will the running time of an algorithm increase? Mathematically, we should not be machine dependent. Now I told you that if we have machine dependent, then there is a problem. Different machines will give different execution times. And if you now even have this, if you sort of just count the number of statements, again it will be language dependent. So what I'm saying is, I'm saying that rate of growth, it gives you a tool. Okay, so this gives you a tool so that you can quantify how the running time will increase on increasing the input. Okay, so let's suppose we'll now quantify them as functions. So this is purely a mathematical concept. So how the rate of function will be, let's suppose we have say 1 means constant. We write 1 as constant function. So 1 is constant. So this means no matter how much input you give, the algorithm still performs in the constant time. The runtime algorithm does not increase or decrease. Okay, this is constant. This is called as constant growth. Then we have something called as linear growth. So linear growth means if you increase the input linearly, it will also the execution time will also increase. So that means, so this is called as linear. Let's suppose on 100 size input, if it was taking 100 seconds, so then on 200 it will take 200 seconds. So on 300 it will take 300 seconds, something like this. Is called as linear. So this is linear. Okay, then we have logarithmic. Okay, this is called as logarithmic growth. Okay, so what is the meaning of logarithmic growth? If you have, let's suppose, 100 and you say log of if log of 100 is, let's suppose, log to the base 10 is 2, so it will take 2 seconds. So it will be logarithmic. And then if we have something called as linear logarithm, n log n. This is called as linear logarithmic. Okay, and then we have quadratic and square, then we have cubic. So all this is called basically polynomial. So whole of this is polynomial. Then we have exponential, which is, until here we are okay. If our algorithm performs in a polynomial time, like, we are good. But after this, if we have exponential time algorithm, so where it takes exponential time, and then sometimes we have algorithm which take even the factorial time, for example n factorial. This is way worse. Okay, so this is the rate of growth. So what is the meaning of this? So these functions will sort of quantify, if you increase the input, how will the output increase, how will the running time increase, sorry. So constant means, so howsoever how much soever input you increase, so again it will take constant time always. So there are some for example, if you want to add an element, let's suppose you want to add an element in linked list, so it doesn't matter how much data you have, it will still take the same amount of time. So a linear time, let's suppose you want to find an element in array, you want to find an element in array which is unsorted, you will take linear time because you will have to go to every element. Let's suppose if each element takes 5 seconds, so if you have 5 if each element takes 1 second, if you have 5 elements, so it will take 5 seconds. Now if I increase the size of array, so what will happen is it will take 10 seconds now if I have 10 elements. So that's the linear time, because you will have to go to the each element. What is logarithmic time? Logarithmic time, let's suppose log to the base 2. If you have binary search, you might have heard that you only take log and steps. Okay. And what is the this linear logarithm? There are algorithms like that. Linear logarithm like sorting algorithms, they take this much amount of time, this much rate of growth is there. That is, if you increase the input, and running time will increase according to these functions. So is this rate of functions rate of growth clear?
Yes, sir.
Okay. So what is better? So can you tell me, is n better or log n better? I'll just have
Login.
so your homework is to compare a rate of growth. So whatever we saw some classes of rate of growth, and we saw some class of functions. You'll have to compare these and show which is better, and mathematically which is better. Now we have all the tools, at least, by which we can analyze the algorithm. Now we also have this rate of growth. How does a function, or how does an algorithm behave on increasing the input? We also saw what's the model of computation that we assume, and then let's see how to analyze the algorithm now in terms of time complexity. Okay. So even all the algorithm that you can see as a mathematical function, the whole point of algorithm is a computational procedure. Maybe it will involve some functions, and we can sort of write a mathematical function for that. Now there are three scenarios where we analyze this algorithm. The first is called as worst case complexity, and we'll say in the worst scenario how much time will the algorithm take. Okay. Then we'll say what is the best case. Then another one is average case. These are three scenarios that we will analyze the algorithm on. Okay. In general, the first case is called as best case. Okay. This is the best case where we will see it. The best case means at the least, if for let's suppose if we are using a sorting algorithm, so if an array is already sorted, so how much time will it take? It will take constant time because it's already sorted. Okay. It will just take one iteration to see if it's sorted. That's the best case. So what's the worst case? If it's in reverse order, that's the worst case for an algorithm. Okay. Average case somewhere lies in between that. Okay. What is the worst case? The worst case, it defines the input for algorithm takes the longest time. Okay. So a scenario where algorithm takes the longest time. Okay. So what's the best case? Best case means it is that input or the scenario where the algorithm takes the least time. Okay. I'll just copy this. Too lazy to write. Scenario where the algorithm takes least time. Okay. Then what is the average case? It provides a prediction about the running time of the algorithm. Okay. If you run algorithm many times, so what is the at average, how much time does it take? Okay. So average, you know what average means. So average means you run it a lot of times and then you take the average. Okay. So here we assume that input is random. Assume that input is random. So again, to read, what's the worst case? So this is the case where you take input such a way so that the algorithm takes the worst time, algorithm takes the longest time. So in terms of sorting, if you have to sort something in ascending order, let's suppose your input is in descending order, so now it's the worst case possible for the sorting algorithm. So if you have to sort something in ascending order and you give it in descending order, so what's the best case? So if you have to sort something in ascending order, it is already in ascending order. Okay, that is the best case for an sorting algorithm. So what is the average case? Average case basically means you run the algorithm many times on using different inputs, and then you see the distribution in general. Okay, this is the distribution that I get. So basically, it assumes input to be random. It's not a specific structure. So this sometimes is called as lower bound, and this is called as upper bound. This is called as lower bound. But these are not the same concept though. But they are interchangeably used somewhere. So we'll say this is average bound. So we'll say we have average bound. Bound basically means till what point does it go if something is bounded by something. Okay, so we have lower bound and average bound and upper bound. So average bound is less than equal to upper bound, and this is greater than equal to lower bound. Okay, is this clear? Is the worst case, best case, and average case clear?
Yes.
Okay, if this is clear, now we'll go to how to now mathematically write this in a notation format. So that we call as asymptotic notations. So we call that as asymptotic notation. Asymptotic notation. How much time do we have? We have enough time. Okay. So now we have this average, we have this best and worst cases, and for all these cases we need to identify what is an upper bound, what is a lower bound, and how to represent this upper bound and lower bound. Okay, and even I told you that each of the algorithm can be thought of having a rate of growth, following a rate of growth function. Okay, and now we have some notations. The first notation which will sort of capture the upper bound of the function, we call it a big O notation. Okay, we have big O notation. Okay, this is not for the worst case though, but people use it sometimes interchangeably, but they are not the same things. But here you just give the bound. Okay, let's suppose you have a function f of n. You have a function f of n. This is some function. This function can be, let's say, 5n square plus 3n, something like this, or maybe 5n square plus 3 only. This is a function. So if you want to bound this function, maybe this function will have a graph. This function will have some graph. Let's suppose something like this, something like this. Okay. Now we want to bound it. You want to show a function which is always after a point greater than this function. So maybe I'll draw a function like this. So after this point, if you see, this blue curve is always greater than this pink curve. Okay, so this blue curve, let's call this blue as g of n, and this pinkish curve f as f of n. Okay, so this is the function. I have a graph of this function f of n. Then I said, like, after a point, okay, this g of n always surpasses the value of f of n. This is always greater than this. Okay, let's call this even c times g of n. Let's say this is g of n, and we'll multiply it with some constant factor c g of n, and let's call this point as n naught. Let's suppose after this point n naught, this c multiplied g of n is always greater than this f of n. This we call as upper bound. Okay, this c g of n is called as upper bound then. Okay, so this gives, like, what is the function which bounds it. Okay, we can have a function different. We can have this function also. So this function also will be an upper bound. So this red curve. So if I have to write it the big O notation, so this big O notation says that if you have a function and you want to bound it, you want to give the tighter bound of it, what is the function which bounds it at the upper side? Okay, well, that function is called as uh, uh, upper bound function. So we have function f of, let's suppose we have a function f of n. If we have a function g of n, so we call f of n is order of g of n, big O of g of n. When do we say this? If f of n is less than or equal to c times g of n for all n greater or equal to n naught. Mathematically, I wrote this. I hope that you understood this thing. So I'm saying we'll say this g of n upper bounds this function f of n. This is the upper bound of this function f of n. Why? When? So when we have this function, okay, and this is the function that we have, this g of n. So this is the multiplying factor c, and when this is always greater than this function, okay, always greater than this function f of n after a certain point n naught. That's what I wrote mathematically. I said f of n is said to be big O of g of n. Okay, g of n means it is upper bound of this f of n. So when we have this f of n is less than or equal to c times g of n for all n less than n greater than or equal to n naught. Is this clear?
Yes, sir.
Nice. So I'll take an example to clarify this. Let's suppose we'll take an example. We have a function f of n that's equal to 3n plus 8. Let's suppose this is our function. And if we want to see a function, we have this 3n plus 8. We want to come up with a function which is greater than this. So I can come up with a function which will be greater than this. So I can write multiply by n. Let's suppose 4n. Okay. Don't you see over here that if I give for, let's suppose n is equal to 1. Let's suppose I'll start when n is equal to 1. So this will be equal to 3 multiplied by 1 plus 8. So this is 8 plus 3 is 11. So 11 is not greater than 4. Okay. So even if you now give the value at n is equal to 1, this does not follow. N is equal to 2 does not follow. N is equal to 3 and it does not follow again. N is equal to 4. But after a point it will follow. For example, I think n is equal to 4 is 12 plus 8 is 20. 16, no. N is equal to 5. Maybe n is equal to 6. So from n is equal to 6, this function will always be greater than this function. Okay, so we can say that this 3n plus 8 is always less than or equal to 4n. This n is our g of n now. This is our g of n. This is our f of n. Okay, and now n naught here is 6. And this is our c. So you can see that this n function is always greater or equal to this function after n naught is equal to 6. So we can say that this f of n is bound by this. F of n is order of n, because n is the function. Even you can say order of n square also. Why? Because n square obviously will bound it. Okay, but we give the tighter bound. Tighter upper bound means, so this is the tighter upper bound. Okay, you cannot give only 3n. Why? Because it won't be always equal to this. That's why we give just one greater than that. That's 4n. Is this clear? So here c is equal. So in this example, c is equal to 4, and n naught, I think at 6 is 18, 24. I think it's better to take 8 value. 8. This like the c and n naught can take different values. How many of are you with me still? Are you already feeling sleepy?
No, sir.
Okay. Second example I'll take is, let's suppose I have a function f of n which is equal to n square plus 1. This is the function, and I want to find its tighter upper bound. So upper bound can be like, there can be different upper bound. I can directly give order of n5. So this is its upper bound. But I want to give a tighter upper bound. What is like nearest to it, which bounds it? So what I have to find is, I say n square plus 1. I'll have to find something which is less than or equal to this after a certain value. Okay, that's what I want to find. So can I write this as 2n square? Can I write this 2n square over here? Because if you see, if I take value 1, so this will be 2, this will be equal. So if I take n is equal to 2, and now you see that this value becomes always greater, and from n is equal to 2. So from n is equal to 2, this value always becomes greater. So n is equal to 2 here, and c is equal to 2 here also. Okay, and this now becomes, so this function f of n, I can write this is order n square. And even you can write order n cube also, but this is the tighter upper bound if you want to give tighter upper bound. Okay, and we ignore these terms, like we ignore this 2 and other things like that. So just because this is the function, this n square is basically the function. So this is our g of n, and this is our c, this is our f of n, and we see after what value does it always surpasses the value of the function, that is over here n is equal to 2. Taking one more example so that it becomes clear. So let's suppose we have n to the power 4 plus 100 n square plus 50. This is our f of n. Now I want you guys to do it. So this is our f of n. So what is the value like n4 plus 100 n square plus 50? So which function is it bound by?
n power 5.
N power 5 is also a good answer, but I want a tighter upper bound.
151 power 151 n power 4.
N to the power 4 and what? 1?
151.
151. I think yes, this is also a reasonable answer. 151, and there are mathematical approach to find these values also, where you can find the closest tighter bound. But I think this is also a good answer. Like where you said that this is 151 n to the power 4. Even you can just say 2 to the power and 2 to the power, because this is the highest term. Okay, and now it is having constant 1. You can just multiply it with 2. Okay, now c is equal to, and after what value will it surpass, that you will have to see. After what value, I think like roughly I can say n naught is equal to 12 or something. So after 12 this will surpass it again. But your answer was also good. 150 or 151 you said, and 4. That is also a boundary. Here c is 150, and then you will have to find, I think, n from n1 it will surpass the value. Now you can write this for this function. What is the worst case? You can say order of n4. Not worst case, I say I'm saying what is the upper bound of this big O notation, that is n to the power 4. Simply, if you have to see, so what you in the upper bound case, if you are given a function n to the power 5 plus 10 and 4 plus 3n, so without even computation you can directly say this is bound by the function order of n5. You remove these terms. Okay, this is like an example. For example, if you are going to buy, let's suppose, a car, you're going to buy a car, and along the way you also ate some chips. So if somebody asks you, so where were you are saying I was in a market where I had to bought a car. You won't even discuss the chips, because chips has a very less price, and here the let's suppose cost was 10 lakhs, and here it costed you so 15 rupees or something. So this is very less if you see it in comparison to these 10 lakhs. Similarly, these terms can be omitted, because this is sort of engulfing all these terms and n to the power 5. That's why in the worst case, whenever you see something, so whenever you see a function like this, you see, let's suppose insertion sort takes something like this, n log n plus 2, and let's suppose plus 4 c1, something like this. You'll directly write only this term. You'll say I'll omit these terms. Okay, because after a while this function will again surpass with some c and n naught. That's why I say that this c comma n, they are not, n naught are not unique. I hope that this upper bound and big O notation is clear. Is the big O notation clear? What is big O? It captures the upper bound, and if we want to capture the tightest upper bound. The second thing that I want to introduce is big omega. Big omega. That's written like this. So this tries to capture lower bounding function. So lower bounding function. Okay. So what is this? So if you have this function f of n, so we try to find a g of n. Okay, if I'm saying f of n is lower bound by the function g of n, when will this happen? So if this g of n is always less than this f of n after a certain point. So graphically again showing you that. So if we have this f of n, let's suppose with the blue, so this is our f of n, something like this. So g of n means something like this. So after a point it's again less than. So from this point n naught, it's always less than this function. So this function over here is f of n, and this red function here is g of n, or c times g of n. So I'm saying if a function g of n is lower bound of function f of n, so what's the meaning of that? The meaning is that this function will always have the less value after a certain point n naught. So to capture this, write it mathematically, I can write f of n will always be greater or equal to c times g of n for all where n is greater than n naught, some value like this. Okay, for this is the value n naught over here. Now we again understand the example so that can write. So what is the lower? We are computing lower bound. Let's suppose our function f of n is equal 5n square. Now we want to compute the tighter lower bound. So I'm saying f of n square should always be greater than. Okay, what is the tightest lower bound? So let's suppose I'll write n square, and what's the value of n square? I'll write 4n square. Like, do you agree over here that 4n square is, but this 5n square is always greater than 4n square?
Yes, sir.
After the value, like n naught here is even, it agrees from value 1. So c is equal to 4, and this n naught is equal to 1. So we can say that this function f of n, this is omega of n square. Okay, now I want you guys to do this example. If we have a function f of n which is 100n plus 5, so what will be its lower bound? So 100n plus 5 is always greater than equal to what? What should I write here? So even you can give me different lower bounds. For example, you can give me root n. Root n will again be the lower bound of this. But I want the tightest lower bound.
100 and
Yes, 100n. Okay, so if I have to write it in terms of the notation, I'll write this. Okay, I hope that this lower bound is also clear. Again, upper bound gives us the function which bounds it from the high, and it gives us a function which is always greater than the function that is our concern. And the second is lower bound. It gives us the function where a function is always lower than the function in our concern from a particular point. Then we have this average bound or average case, which we already saw, and we used a theta notation. Big theta, we call it big theta. We use this notation for that. Okay, so now what we'll do is, if our function is like this, so this is, let's suppose, our function, this is our function f of n, and we want to write this in theta notation. If we want to write its bound, so we want to find a function, let's call it g of n. We want to find a function g of n such that this g of n after a certain point is greater, okay, and the same g of n multiplied with some other constant, okay, and it should also be lower bound of this function. So here let's call this c1 g of n, and here it should be c2 g of n. If we find such a g of n with c1 and c2 such that it bounds the function from both the sides, it bounds the function, let's suppose, from the bottom and from the top, so we call this as big theta of this. So f of n is said to be big theta of g of n. Okay, we say that this is the average bound. Usually we use it for average bound. So we say if we have a function g of n such that we have two constants c1 and c2 and they bound the function. So mathematically, how we can write it? We can write f of n is less than equal to, let's suppose, c2 g of n, and this is greater than equal to c1 g of n after some value. Let's suppose this value, we'll call it n naught. For all n is greater or equal to n naught. Okay, this is big theta, and most of the times you will use this big theta for analyzing algorithms. Is it clear?
Yes, sir.
Okay, and now I'll leave the mathematical details here, and now we'll go to C and like real algorithms and how to analyze these. I hope this much mathematical detail, I have enough bored you by giving the mathematical details, but these are necessary. You won't understand them in the first go, and I'll urge you to reiterate them again. Watch it at least like 2-3 times so that you understand why did we sort of have this mathematical notation. Because the problem we had is this. This is our problem. So our problem was right here. So we did not have we do not want running time to be machine dependent. We do not want our running time to be dependent on the number of state programming language. So we wanted some mathematical notion. We wanted something which we can capture so that we can give a metric based on which we can compare and say how much the algorithm is efficient, or what is how much good is an algorithm in comparison to other algorithms. So that's why we first define the rate of growth, and based on that we also give a tighter upper bound, lower our upper bound. So maybe you can capture worst case by this. You can capture worst case by this big O notation. So if you give a function g of n for algorithm, if you give some big O notation, you are saying this is the worst case and this is how it's bound. So if you say that, for example, order n square, so order n square means this will not go beyond this. Okay, so if you say omega of n square, so this means this is the best case we can have. Okay, this is the lower bound, and then we can give average bound. Most of the times you will see average bound written, because that's what we are interested in. Did you understand the whole crux of the discussion? The crux of the discussion was that we found a way by which we can quantify how to compare these algorithms and how to find their efficiency in terms of the running time. Okay, now let's see how to use this order of growth asymptotic complexity and to come up with the functions and see. For example, if we have loop, let's start with loops because we'll be writing a lot of loops. Let's start with loops. Let's suppose we have something as for I is equal to 0, I is less than 50, or maybe let's say I'll write n rather than 50, I'll write n less than equal to n, then I plus plus, and then I'll write some statement. Let's say m is equal to let's say m plus 1. Okay, so how many times will, because I told you this will assume that it takes constant time. Okay, so how many times will this statement run?
N times.
So this
N
statement
time.
will run n times. So this, let's suppose, takes some constant time c. So what is the function which represents this? So function f of n is c times of this n. Let's give this a value, c value. Let's suppose this c is 4. Let's suppose this constant time is 4. So we'll write 4 times of n. Okay, now can you give me a tighter bound for this? Can you give me some upper bound for this? Can you give me worst case complexity for this? So I can write 4n is always less than equal to what is the n that I can put here? 5n.
5.
So I can say f of n is equal to order of n. So this basically has the worst, or we can say upper bound as order of n. This algorithm is big O of n, we can say. Okay, now again using the nested loops, let's call this nested loop. So we'll have for, let's suppose this runs n times, and then we have for this runs m times. So this is, I'm writing in the pseudocode format, so you can write the this loops in your language, preferred language. So this is our first example. While we have only one loop, now we have for loop, and within the statement, let's suppose we have a statement m is equal to m plus 9, and then we n is equal to, it's not even this m and n should be different, and p is equal to p plus 2 r plus s. Let's suppose this takes c1 time. Let's suppose this takes c2 time. Okay, some constant time, because that's the assumption we are holding. So how many times will this statement run? So how many times will this statement, which takes c1 time, this statement, how many times will it run?
C1 times n into m.
N into M, yes.
Yes, so it will run n into m times. So c2 again, so we can write this will run n into m times, and then c1 plus c2. So this is, so this will be c1. Maybe we'll call it a bigger c, both of these a big c. Okay, so this is n into m c. So we have now a function. If we had this also as n, okay, if we had also this as n, so we can write this as f of n is equal to some constant times n square. Okay, so now our f of n is some constant n square. Let's say this constant is some constant 5. So what is the big O of this? What is the big O? How can I give the upper bound of this? So what can I write here? N square obviously will be there. So what should come here?
6.
Some 6. Okay, so we can say this nested loop, it basically takes order n square time. Okay, now if we have some consecutive statements, let's suppose I'll write something like this. So this is in the example. Some other example I'll take. If I have x is equal to x plus 1, this is my first statement. Then I'll write a loop which runs, let's suppose, n times. Then we do some operation within the loop. That there is some w is equal to w plus 2. This is one, and this is our one loop. Then we have, this is our one loop separately, and then we write nested loop. Here I'll write nested loop. Now I'll make it a little bit complex so that you know how to form this f of n and then how to form this bound. So now I have for this runs, let's suppose, n times, then for this again runs n times, this is nested, and then we have some statement over here, k is equal to k plus 1. Okay, so this will run constant time. Let's call this c1. So this is c2, and this will take c3 time. Let's suppose these are 3 constant time. Now how much time will this block take? How much time will this block take? So this will take c1 plus n times of c2. Is it clear? This block will take c1 plus n times c2 time.
Yes, sir.
So how much will this block take? So this block will take c3 n square. Okay, this whole block. Are you following me? So
Yes,
then
sir.
we can write f of n is equal, we can just add these things up. We can say c1 plus n times c2 plus, or maybe c2n, and then we'll write c3n square. Maybe these are some constant value. Let's give them some values. Let's say 4 plus 5n plus 2n square. Okay. So now if I have this function, so if this is my function now, okay, if this is my function, so if I want to write its upper bound, so what I can do is I can write something which is an n square. So what will be, what should I write here? Maybe 3.
3.
Okay, so here this is the algorithm that we wrote over here. This is order n square. Directly, even without even saying this, I told you to omit these other terms and just keep the bigger term over here. Okay, so can you now, like, if I give you some example, will you be able to give me the answer? Let me give you an example. So I'll see, will you be able to do it? I'll just pause the recording over here so that it does not appear in the recording. So
C2n
what I'll write, give me f of n, that is c1
n square
n square plus
plus C2n
c2n
plus C3
plus c3
plus C4n cube.
plus c4 n cube. Beautiful. Okay, so if you have a code like this, will you be able to analyze it now if it is full of for loops? So here I gave a for loop. The first was nested for loop, so obviously it will take n square time, and here we assume this is constant, and then this c2 will only run for this for loop, the outer for loop. So that's why we wrote c2n. Then this is a constant again, so it is added as c3. Then here if you see, this is 3 nested for loops, so we wrote n cube, and here one statement actually we wrote cn4. So can you just give me the upper bound of this? So we can write order of what?
Order of n cube.
N cube, because we will just remove all these terms, so we don't need these terms. Okay, I hope that you will be able to analyze these things. Now I'll give you a little bit harder problem maybe, and I'll see if you understood this.
Log base 2n.
Nice. So who said the answer?
Zakir.
Nice. So why did you call it log to the base 2, log n to the base 2? So why is it so?
Because sir, I is iterating from 0, it won't go to n. It is doubling each
In
each
each iteration it is doubling
doubling
by.
twice.
Really nice. So what happens is it will first start with for, let's suppose, here it will go into the infinity loop if you see. So this basically is actually wrong. So this will run infinite times, because it will I is equal to I. I don't think it will go infinite times. Sorry, because we are iterating it I plus plus. Yes, yes, you're right. You're right. So I was hoping that this I is equal I multiplied by 2 is 0. But in the second iteration it'll obviously. So what he said is like this. Here first it will have we have is equal 1. So I is equal to 1 in the first iteration. So in the second iteration it will become 2. In the third iteration it will become 4. It is doubling every time now. So in order to reach n, so how much iterations will it take? So if we have to reach n. So how many iterations will it take? First we'll go to 1 to 2, then 2 to 4, 4 to 8, and it is doubling. It will take log n iterations. So these many number of times will this run so that it will stop. Really nice. So I'll give you some formulas so that if you have to compute these things and you'll know all of this stuff. So I'll just give you some formula, because these are frequently used formulas and maybe some of you might have forgot them. I'll just write them. So if you have summation of 1 to n of k, so this basically means 1 plus 2 till, let's suppose, n. So this is equal to n into n plus 1 by 2. Okay, summation of an arithmetic series. So if you have a geometric series is something like this. I is equal to, this is k, this is I, let's suppose. So this is I is equal to 0 to n x to the power I. So this is 1 plus x square, something like this, xn. So the formula for this is xn plus 1 minus 1 divided by x minus 1. Okay, this is our arithmetic series, this is our geometric series. This is basically summation of these. Then we have something called a harmonic series. So the summation of a harmonic series, if we have a series something like this, x is equal to k is equal to 1 to n. So this is 1 plus 1 by 2 plus and so on till 1 by n. So this is log n. This is nearly log n. Okay, this is the summation of harmonic series. Then we have other formulas as well. So here, if you see this, if you have summation of log of k, this k goes from, let's suppose, 1 to n, so this is equal to n log n. Okay, one more formula that I can write is summation of k to the power p, where k goes from 1 to n. This is for example 1 to the power p plus 2 to the power p plus 3 to the power p, something like this. This is nearly equal to 1 divided by p plus 1 n p plus 1 and raised to power p plus 1. You sort of write these formulas somewhere so that whenever you analyze the algorithm, and these will be used. And then for the logarithms, what we have, we know that these are basic logarithm formula. If we have log of x raised to power y, we can just get the power down. So this is y log of x. So if we have log of n, this is log to the base 10. So if I write something log to the base 2, and there is something called a natural log also. Okay, so if I write only log n, this basically means this. So some other formulas, log of xy, I think this is log of x plus log of y. Correct me if I am wrong somewhere. So log of x by y, so this is equal to log of x minus log of y. Okay, and what are the other formulas? And these things are enough. Okay, so these are the formulas. This is our arithmetic series, this is our geometric series, this is a harmonic sum, and these are some formulas which I wrote over here. So if now given any algorithm, you should be able to analyze the algorithm. Okay, so only thing that I left is if else statements. Maybe I'll also go through, because we saw the loops, we saw nested loops, and if there is a program which considers if and else. Because now what does the program consist of? Program consists of either for loops, if else statements, and the constant time statements. So for loops we saw, if there is a nested for loop, what to do. Now if we have an if else statement, okay, so what will be the worst running time of this? So what we'll do is we'll analyze both if and else part. So whichever takes the most time, we will take that. For example, if we have a part of if over here, and if, let's suppose something, and there's a condition, if, and then there is a condition, some condition, and let's suppose within the if there is a if block, we call it an if block. Let's say there we have for loop, this runs n times, c is equal to c plus 1, something like this. Then we have else. Okay, then again else block, and in here we have for, this runs n times, and the for which runs n times, some q is equal to q plus 1, something like this. So what I said is, in if and else case, if you see the order of this if block is order n, okay, or the complexity is n. So here this is n square. So I said take the maximum of these two, because eventually one of this will happen. So either if will be executed or else will be, both of them will not be executed. So you won't have to write n plus n square. This is wrong. So what you have to do, you will have to write the worst case. So this is the worst case, n square. So you'll just write n square for this. Okay, because this won't, either this will get executed or this will get executed, and we are being safer, and we are saying that, let's suppose most of the time this will get executed. So we'll write n square for this. Okay, so what will be the exact function? F of n here will be, let's consider this as c2, so c2 n square. Okay, and the worst case complexity, or the big O notation, will be order of n square. Is this clear? How to, if we have an if else statement?
Yes, sir.
Okay, so now again I'll give an example. So if I have a for loop for I starts with n, I is greater than, let's suppose, equal to 1, okay, and I plus plus, let's write this, and here I is equal to I, let's suppose, divided by 2. So I think Zakir gave the answer. Now Zakir, you don't have to give the answer. The other people, can you give the answer for this? How many iterations
I
will
guess
have? Let's suppose this is C1.
log n will be the answer, I guess.
This will run log n times. How do you have to see them? So because the point is, you are starting with n. So for in the first it will be n. Second time it will be n by 2. Third time it will be n by 4. And you are decreasing it, and you have to decrease it 1, and you have to see how many iterations will it take to go to the 1. Okay, so how to write it? So you can say basically this is going from n, then n by 2, then n by 4. Each time it is decreasing by 2, and I have to reach 1. Okay, and how many steps will it take? It will take log n steps. So even you can count these steps mathematically, but here you directly can say that this takes order, because how you can write it, because you want to get it like this. So you can write this n as, let's suppose, 2 to the power something. So say you have to get to 2 to the power k, let's suppose. Now if you apply the log of this, log of 2 to the power k, and let's say this is log of n, and then we'll say it k log of 2 by using the log approach, and this is log n, and how many iterations will it take? This is log n approach, log n. Okay, log 2 basically means 1, so log 2 to the base 2 is 1. So this is how you can mathematically derive it. I don't feel like it's really easy for you people now, and then we'll go on, if there is time, we'll go on the Master's theorem also. I think we can stop the recording over here, and if you have any questions related to any of these concepts, and in the next class I'll take the Master's theorem, and we're done with the complexity, and we'll take the arrays then, the next topic.